To handle wind-disturbed flight, we propose GustPilot, which combines a learned DRL, deep reinforcement learning, based velocity planner with an INDI, incremental nonlinear dynamic inversion, controller for robust navigation and stable tracking. The figure illustrates the value of learned low-level control. Under the same wind disturbance, the conventional stabilizer loses balance and leads to failure, while the learned stabilizer compensates more effectively and keeps the quadrotor stable. Our system uses a two-level architecture. At the high level, a DRL planner receives the quadrotor state together with the gate information and outputs reference velocity commands for navigation. At the low level, an INDI controller tracks these references using outer loop velocity control and inner loop attitude control, then converts them into motor PWM commands through a mixer. The framework is trained in a GIM-PI bullet environment with wind disturbances and then transferred to real flight experiments for robust autonomous navigation. In this scenario, the wind was disabled for both controllers, and the experiment was conducted with 6 gates of different orientations and altitudes. DRL-PID achieved an overall success rate of 85.5%, with a peak speed of 1.0 meters per second. Although PID successfully completed the mission, it collided with the gates twice, specifically at the 2nd and 5th gates. In contrast, DRL-INDI achieved a higher overall success rate of 98.8%, while maintaining a lateral gate center root mean square error of 0.127 meters and reaching 1.337 meters per second. This shows that even without wind, the INDI controller provides tighter tracking and more agile flight. In scenario 2, the same flight setup was used, but this time with distributed wind disturbances. DRL-PID achieved an OSR of 0%. In all cases, the drone lost stability after entering the wind region. DRL-INDI, however, maintained a high OSR of 97.2%, with an RMSE of 0.11 meters and a maximum speed of 1.35 meters per second. These results show that INDI remains stable and agile even under significant wind disturbances. In scenario 3, 4 gates were used, and a high-speed fan jet directly crossed the flight path. DRL-PID achieved an OSR of 58.3%, with repeated failures near the end of the mission, and in several attempts the drone crashed at the last gate. In contrast, DRL-INDI achieved a much higher OSR of 92.5%, with an RMSE of 0.11 meters and a maximum speed of 1.122 meters per second. This confirms that INDI handled the strong jet disturbance more effectively while maintaining stable and in scenario 4, a moving gate and a moving fan jet created the most demanding test, requiring continuous replanning and real-time disturbance rejection. DRL-PID failed to complete any trials in the nominal setting, with an OSR of 0%. Even after reducing the speed command by 30%, it achieved only 31.37% OSR, with slower and less accurate flight. DRL-INDI, however, adapted successfully to both disturbances, achieving an OSR of 90.0%, with an RMSE of 0.125 meters and a maximum speed of 1.311 meters per second. This demonstrates that INDI can maintain robust and agile flight even in the most challenging environment. Under hard collision conditions, the DRL-INDI controller showed fast recovery and quickly regained stable flight. This highlights the strong recovery capability of the low-level INDI controller, while the DRL policy continued selecting acceptable actions even inside the turbulent core region. In an additional scenario, we applied a vertical wind source along the flight path to further test the proposed method. The system remained stable under the upward wind disturbance, demonstrating the robustness of our approach to vertical aerodynamic perturbations. Across all 4 scenarios, DRL-INDI consistently showed better robustness than DRL-PID, with higher completion, lower tracking error, and better performance under strong wind disturbances. The largest differences appeared in the more challenging wind scenarios, where PID often failed while INDI maintained stable flight. The results also show strong generalization, since the policy transferred from a simple training setup to more complex environments without retraining. In future work, we will explore tighter RL-INDI coupling, online wind estimation, and adaptive gain tuning. Thank you for your attention.